Okay, so we're gonna get started. So for today, I think we will, first of all, just keep discussing the paper. And there are a few, we talked about certain questions that we should go through, but as I was going through, the particular, like the Moodle post that you guys made. So feel free to jump in with any other like extra questions, because I think all of those are great. We just need to probably like keep track of the time, and so we don't go too much over time about all of this. Okay, so give me a second. Just want to bring up the slides really quick. Okay, so last time we were talking about certain part of the question, certain parts of it. So we're going to continue. We started with the discussion about the two simulation schemes that produce different results. So I added this at the end about these two simulations. And I still have doubts, to be honest. Like reading the responses, I got a little bit even more confused. So I don't think I have a good answer at the moment, but we should definitely talk about it, because obviously something needs to be talked about. Okay, so maybe just before we start, I just want to maybe voice my concern, like what I didn't understand, say, like from the discussions. So if you look at the paper, really quick, I mean, I understand that they're trying to make the point that the conditional is going to carry more information, which I understand, especially from the two figures. You see that one is doing better than the other. But I was still having a hard time understanding equation 2.9 and 2.11. I mean, I understand they're trying to take the average, and I also saw some of your comments about the figure 3, the simulation scheme over there is using more samples. Okay? But for me, to be honest, I just don't see how that is true based on like the equations. So I can tell you a little bit more about what I thought and just correct me. So based on 2.9 and 2.11, I thought you are still just using the last like draw from each chain, right? Because when they're taking the average, they're taking average across I, and I goes from 1 to m. Okay, so m. So let me just fill in like a little bit background here. So both of these two simulations are looking at k equals to 10 and m equals to 500. Okay, so that means they run 5 different chains, and each chain has length 10. Okay, so that's how I understood it. So say, I understand for the first figure, like the simulation over there, they run it for 500 times, and so they have 500 draws in the end, because they're only taking the last draw from each chain. So they're like just plotting it directly of x in the, let's see, in the black beans, and then in the white beans, it is from the truth, like they're doing a Monte Carlo over there. So for figure 3, based on what they're describing in the paper, my understanding is they're still only saving the last draw from each chain. So in the end, they only still have like 500 draws. That's how I understood it. So some of the comments from Moodle were saying that because now you're using more draws. So I guess what you're trying to say, my guess, I don't remember who said that, but my understanding is you're trying to say that now you're not only just using the last draw from the chain, you're trying to average things out, which I mean, to be honest, I just don't see it, but I don't but I also saw like some of you follow up about this, saying that, oh yeah, because you have large sample size, it's more like converging to the truth, etc., etc. So I just want to like voice my concern, because that's not what I see, but I'm still not understanding entirely how like the second way is actually doing the average, while the first one is only looking at the marginal. Yeah, that's still what I don't understand. So I want to just voice out before like we spend like maybe 3 to 5 minutes in groups, so you can talk about this. But also like some other comments I was trying to write down from that discussion is there like any better theoretical explanation using the conditional than just showing it like empirically? So that's another comment, which I guess That's what the textbook is, like, sorry, not textbook, the paper is trying to say. So that particular last paragraph, when they talk about, because based on like Rao-Blackwell theorem, illustrated in Gelfand and Smith, as well as like by Liu, Wang, and Kang, I think that's the point that they were trying to say, like even theoretically, it should carry more information. So in the simulation, you should see that. So I think for that particular comment, that's how I thought about it. And I think it's Richard also brought up the differences of these two simulations, or like the figures. Is in the figure 1, they're plotting the counts, right? And then in figure 2, they're talking about like they're plotting the probability. So that's a difference, of course, yeah. But again, I think the general shape wouldn't change because you're just dividing the total number of draws that you're doing. So those are the ones that I found based on that particular discussion, like from the forum. I really enjoy reading all of them, but that just I'm just even a little bit more confused based on what I understand. So let's spend like 3 to 5 minutes again, just break into teams. And you can, I mean, I don't think I'm understanding it correctly, so I just need more input and then about all of this. So please start, and I will walk around, join I can. But of course, so we're gonna spend a few more minutes after the like group discussion as a whole about this, and then move to question 4. And then some other questions, because I think there are some other about other questions that we haven't got the chance to talk about yet. Okay, so spend 3 to 5 minutes about these 2 simulations. I hope just now what I described was clear, like my concern. But just you can definitely like say something different. Maybe I can probably miss something. Okay, so let's hear what you think. Okay. Right. So let's hear what you think. Maybe just feel free, I guess, to address maybe like particular issue that I raised up, but you can also talk about this stuff. So yeah. Anyone? I will just bring the iPad to you so I can record the material better. And also, what I realized last night, remember, like I got kicked out from the iPad, and then after that, all the voice was gone. Yeah, so it was a little bit unfortunate. I think like 30 minutes of material didn't get recorded. So this time, like you see like something acting weird, just let me know. I need to re-sign in. So last time I didn't sign in and I mute that one, so nothing was recorded after like, I don't know, 15 minutes. Yeah, so today just, yeah, you also like, yeah, help me with like monitor that as well. All right, so what do you think? Yeah, I'm just gonna bring this to whoever wants to talk.
I'm not sure if it's right, but so I think, so figure one, you take for each of your 500 chains, they're taking, I think, just one value from each of those chains.
From the end.
Yeah, and plotting it. And I think in figure 3 instead, they take all the final values of all 500 chains, they average that, and then they use that as a density, that value as the density function.
So they average based on?
They just average them all, average all of the final values in the chain. And then they just plot a density function, so you're not taking.
Oh, okay. Right, because I mean, they're definitely like averaging like step over there based on, but it's still going to be 500 draws for each case, right? Okay.
Just to think about how you use a value as a function.
Yeah.
In that statement, like I kind of get it, but I just don't understand how like you would average it and then just get a function.
Right. So if we actually look at 2.11, I guess, guess, because that's mostly most directly related to the stuff. So they're averaging, okay, so they're averaging conditional, but the conditional is just what we have, right? Because you draw, say, the last x based on the previous y, whatever. That's from the Gibbs template. So my understanding is, and they're taking the average of different yi. So I think that's how they're, like, your question is like whether you can take the average of the points, or?
I'm just not exactly sure how you transfer from having all the different x's to getting the conditionals, like summation equation.
Right, good point. So what's the draws? Like the draws, they are, I mean, say the last chain, like the draw from each of the chain at the last point is conditional. I mean, it is a draw of x, of course, but it's a conditional of x given the previous y. Right? Yeah. So I think all of the draws. So even though we do have the draws, they're actual values, and that's what they're plotting in figure 1. Yeah. But my understanding, and I'm still not sure, like the figure 3 is you're getting the draws, but the draws, if you think about it, is still conditional. It's conditional draws of x given y after the chain is converged. Like they run it for like k equals to 10, like 10 iterations, and they say it's gonna like be good enough, so they take that. But still, if we look at it, 2.11 is still like talking about like what Eli was saying is density plot, right? Because you're averaging not just the point itself, you're averaging of the conditional probability of x given x, the capital X given small x, x given yi. So what do you think that probability is? Like, is just a density or?
I guess this is a question. Can we go over again what M represents? That's, I think, the biggest thing that I'm struck with.
What M? What is it?
I thought M was the number of chains.
Yeah. So they start,
it's 500.
right, so they have N, which is 500 different chains, and each chain is run for 10 iterations. So each K is 10. Yeah, for both cases, yeah. And then M is 500. So it's always at the end of the chain. So how can we understand this 211? Like in particular, like it's I mean, mathematically, I understand it's the probability of x given y, and then we're averaging that probability across all of the chains. Yeah. So pretty much, I guess every chain we get a probability. So how do we get that probability? Because we get draws. I guess that's what I think I echoed in Serena as well. Like, what is? They should have provided more information, I think. But yeah, to me, I understand they're trying to average, but at least right now, I think we know that it's not averaging. Like we're not taking the average of each chain, right? So from each chain, we're still getting the probability. But what is that exactly? What do you think? I mean, we might not talk about the answer to be honest, but if you have some ideas about how that is come up.
But do we have the right equation of this conditional probability or no?
Sorry?
Do we have the equation of the conditional
probability? The equation of the probability.
The conditional.
Oh, so you're saying that it may be from 2.6 A and B, like that. So if it's y, okay. So if it's okay, right. So okay, good point. So if it's x given y, then it's gonna be 2.6a, right? It's the binomial over there.
So we just have to plug the value of the yi into this equation.
Right. Okay, because that's giving us the probability. Right? We're evaluating x given y with different y values. So if we at the end of each chain got values of y, like one value of y, and then we put all of them together and then try to evaluate x given different y's. And then in particular in 211, it is the probability, the density that they're evaluating. So it's probably, 2.6a, which is that particular binomial over there. So n is fixed. Y is different from each case. We evaluate, so it's going to be the choose function and all of this in R. And so it's probably going to be D by norm, right? You use D by norm. You evaluate all of them, take the average across 500 chains, and then that will be the density of what you have. Agree? What would n be? Okay, that's from the question. Let's see. N, I think, is 16. Yeah. So they're right. So for it is all starting from example 1. They're doing this x and y, and they together is going to be a beta binomial. But each of the full conditional, one is binomial, the other one is beta. So I think n is fixed. So you see that n is 16, alpha is 2, beta is 4. They're all fixed for both of the simulations. Okay. All right, so I guess that's solved, which is next. I was really, so I guess we all should have paid a little more attention about what the equation 211 entails. It's really talking about the probability density. So, okay, so that means, so anyone wants to make a comment about the claim that they have in the last paragraph over here? Because they're comparing in figure 1, it's all of the draws of xi, and then you take the average, because that's what you do when you plot just the draw of x. And then in figure 3, you're plotting the expectation of x given y, which is kind of being achieved by this 211 equation. So anyone wants just to like maybe end with the implication of the conditional carrying more information than the marginal? Maybe anyone from that part of the classroom? Or anyone else, that's fine. So I was trying, I'm trying to say, like, trying to get like the end of this question in a sense that, so now we understand, because of figure 1 and figure 3, we see the differences, we see the improvement of using the margin, using the conditional, comparing to the marginal. So, and then they have this ending paragraph over there talking about it. So anyone, I mean, many of you actually made that comment in notes. So someone wants to give a conclusion here, and then we can move on to question 4. Or are we all good about this? Like it's straightforward enough that no one needs to restate it again.
I mean, I see how it works in these figures, but I don't see how it would necessarily always. I don't see that necessarily.
Right. So, I mean, the immediate question that I have, I mean, I totally understand what they're saying, but think about what we do, actually what we're doing when we're summarizing the draws, right? When we're doing it in practice right now, we were not evaluating the density every time, right? We pretty much, so we do the Gibbs, and then in this case, you have x and y, you only have 2 parameters. But if you have multiple parameters, what we do is you run the Gibbs long enough, you pass, like hopefully they pass all of the diagnostics, and at the end, we just save all of the same theta 1, theta 2 until theta r, and then we're just gonna summarize them separately, right? If I'm interested in theta 1, then I might do like a plot of it, I return the mean, return the variance, I get a 95% confidence interval, et cetera, et cetera. So I think in practice, we don't really go that far as 2.11 say, like do all of the evaluations every time we do it. So my question, I guess, when like in this particular comparison, I see the difference, but I feel that in practice we actually don't use that much. We kind of only use the marginal.
Yeah, because in practice you don't really. I mean, it seems to only work if you take multiple chains, which. At least what it sounds like, people don't usually do that. They just run one really long chain.
Okay, good point. So that, because that actually leads not to question 4, which we're going to go back later, but related to, I think, multiple people actually posted about the differences of what was being done before and what it's doing now. Some of you were talking about like what is better than the other, like talking about the advantages and disadvantages, which is good. But I think Eli posed a question like just now, roughly, about like why, like you're thinking about why people in the end do not continue doing the multiple chains. Is that what you want to talk about?
Yeah, well, I mean, I think one of the things that I ended up writing about in this post is there isn't really much of a difference between taking multiple chains and taking one chain and fitting in. You could just think of the one chain as being multiple chains, where the starting value from the next chain is the same as the end value of the last one. So as far as I understand, there's no reason why we couldn't use this technique, considering the one chain as these sort of quote unquote separate chains.
Right, so this is, I think, because like Nick, he's not here today, but he was asking the question last time as well. Like say what Eli was saying is that now if we have a super long chain, you can really just break it because we're doing the thinning, right? And the thinning would be every, I don't know, 10 or 15 straw that we draw, like we say, you can think of it as the starting point of the next one. So you can pretty much just break it into, So what do you think? I mean, the thing is, I feel like my immediate response to this will be, if you start M different chains, you can make sure that they really start at multiple places. Like you can make sure that they start at so many different, because if you're doing one chain, even though you're doing a thing, things are still dependent, right? Because one is based on the other. And even if you do, say, I'm just imagine like, okay, I should do this. I would just thinking about, say, say if I have, like, say, say this is just this should be the correct parameter space that I should explore. Then if I have one chain, like one super long chain, I'll be able to say like start over here and then go here, and maybe this gonna be, I mean, this is really, I did it wrong. I couldn't go back, right? Sorry. Anyway, let's see. Yeah, I'm trying to say that like my chain looks really sticky. I mean, in reality, it shouldn't look like that, but I just want to give a demonstration. So say in this region, in this particular region, we save certain draws every 10 draws or something, and then treat those as the draw that we're gonna use. But they're still like starting around the same region. If you try to argue that, why you should use the multiple chains idea, because if you do it, say if you do multiple chains, you'll be able to start from here, say, and then another one from here, and then you're only saving, say, the last draw from each. Yeah, but I don't know. I mean, that's just another thought, like thinking about how chains are functioning and then how iterations are depending on the previous ones. Yeah.
I think the thing that Nick was saying last time, and the thing that I sort of think about, is that in order for this to be a meaningful practice, we have to assume that if we thin it sufficiently, that it's no longer dependent, so that it shouldn't actually matter where we start.
Yeah, yeah.
And the other thing that I mentioned in the post that I've been thinking about is that the way that our computers generate random numbers is pretty similar to this, at least in theory, as far as I understand. Given that like we have the seed for the random number generator, and then it puts it through a bunch of functions, thins it, and then produces that as a random vector. Right. So if we don't trust that sort of process, then I think that there are a lot of other things that we have to, like just starting from different values, but still using the same sort of pseudo-random algorithm doesn't actually avoid that problem.
Okay, good point. So the thing is, okay, so going back to Nick's point, like from last time, I think Nick was trying to say that because in the end, they should converge to the desired space that we should explore. So it shouldn't matter where you start, right? So I think that's I think we probably all would agree at this moment. But again, I think all of this, we're like talking based on the paper, and then soon, once you do more like Gibbs sampler, you will realize that in reality, like all of this are relevant. All of this are the things that you need to think about. But then, okay, of course, I mean, I'm not saying that you shouldn't do multiple chains. You can just do it. I'm totally fine with that. And I think someone also in one of the posts was saying that, oh, what if we run multiple chains, but we don't only save the last draw? We can do thinning for each of the chain, right? And then we'll still be able to get some good number of draws because we don't toss away so many useful things that we have done already. So all of those are possible practices. I'm just saying that like what I know so far, I think people usually run one long chain and then do the thinning. And then if they want to check if the chains are doing well enough, they will still run multiple chains, but not as many as like 500. like they're probably gonna run a couple or like 10, and then do this Gell-Mann-Rubin diagnostic that I told you about, just to make sure that each chain or the final chain that we're gonna use is good enough. Okay, but a lot of times, my understanding or my experience so far is people are going to use that mostly. But maybe I'm biased, maybe I'm just not knowing what is what are other ways being practiced. But this will be okay. Cool. So I think we solved that somewhat in some sense, and I do want to just spend maybe like 5 minutes in total. Oh, no, 10 minutes in total about question 4. So that one, I think 3 of you responded. So what I'm thinking, So what I'm thinking is, because 3 of you responded, so I assume the 3 of you did give enough thoughts, all of this. So I was thinking, we start with just like the regular, like the way that we group people, because I remember it's Eli, Sean, Kendall, and Elisa. I think all 3 of you responded. So how about like we break into 3 groups, like one of you is the lead over there. So, because I'm not sure why other people didn't respond. I'm just trying to, no. I'm not saying that you should be the one like to report back, but I'm just saying that because you 3 like responded to it. So I was thinking like we're gonna have 3 groups right now, but like each of you gonna be like the person, like each of you gonna be in one of the groups, so everybody can at least hear what they have done. Okay, so maybe we have Eli over here. So just feel free to join whichever you want, and just have a rough even number. If you have a laptop, you can go to Moodle to see what those 3 people have done in the responses. Because this is again something probably beyond the scope of what we have taught so far, or even in the previous classes. So I really appreciate it if you tried this. And yeah, so if you want, you can go to Moodle real quick to see what the responses are. But now we have one of you in the team, so we need to contribute and have a discussion.
So the is why it's just like the way that I read it, I don't know. Again, I'm just reading on stuff. But I literally was just wondering this question. So yeah, exactly. I think basically the idea is that it's mathematically, but it's like the things that we talk about in probability and that you can derive the particle from the two conditionals mathematically, but that's possible. So this is just that there.
That makes sense.
So I think the idea is that first of all, this shows that we can simulate the marginal populations, and second of all, gives us some sort of suggestion as to how to do it. So my thinking is we take this average expectation and just do the same as we want. That can be an approximation. But then there's another result that there is in the second Would fit. I actually just said that.
It's like it's like a sleepover. Just run it so it's yes. So T is the proposition. Yeah, I don't get that either because they just say like the end of X equals where do they get
Where did they actually even say that? I didn't make that up. The way that I interpreted this is probably not it's your value X of X at some other value, which we may represent anyway, like previous values of X.
Okay, let's have maybe one or two comments from this, and then we're gonna end the discussion. But I also just because I think there's still like questions being posed on Moodle, so I will go through them later today to respond individually if I see particular questions that were not being answered. Yeah, just so you know. But what about question 4 over here? So if you think like if the math is too long, that you're not getting a good idea, then just maybe tell us like say the big picture of why they're trying to what they're trying to show in the end. But the section is called conditional determining margins. And that's what we have been doing, right? Like in Gibbs testing, we've been trying to we come up with all the conditionals and then we draw iteratively of them for all of the parameters, and in the end, we say that we should be able to get the marginal distribution just good by using the draws from those conditions. So, anyone? No pressure on the 3 who responded. I mean, it would be nice if somebody else would like to say something about it as well. Yeah, Katie.
So it says that equation 4.1 is the fixed point integral equation. And that's just the combination of h of x of t, which is this product of the marginals, the integral of the product of the marginals, and f of x of t, which I guess is just f of x evaluated at t. And then it like goes on to say how that's another form of the Gibbs scheme. So like when it just like, I guess reiterates how you can use the conditionals to find the marginal, but that's the extent of my understanding.
So 4.2, when they move, to 4.2, they show that this hxt is like, they're showing that like the draws of x from k to k minus 1 is approaching that, which is the hxt, and that's when k goes up to infinity. So they were saying that this particular form, the fixed point integral equation, is going to be a limiting form of 3.5. So if you go to 3.5, you will realize that that's the case. So 3.5 is like showing from the start, right? Like x0 to xt or xk. Yeah, that's what they're doing. So here, I guess, like in a sense, like some kind of like a micro level, you're just looking at the two adjacent draws. But then eventually, if you round the chain long enough, which is about the value of k, you'll be able to get like the conditional will give you the marginal. Okay. Anything else? Or anything, any other thing from the paper itself? Like I said, some of the questions being asked on Moodle, feel free to answer them. I will go through them today, like at least by the end of this week, to make sure that there are some extra questions being asked that we didn't get the chance to discuss. I will try to leave my answer, but again, I don't think my answers will be the best. I think some of yours probably are better, so feel free to jump in over there. Okay? So this paper, so the American Statistician, the journal itself is supposed to be very accessible, and I think it is still. Like right now, if you try to like take a look at that journal, you will see some of the stuff is definitely like relevant and it's viewable for us to read, even as undergrad students. So that will be a good, and we have subscriptions. So if you go to the Math Lounge, you will see that every month we have, no, not every month, every 3 months, I think, every season we have like a journal from this particular journal, we have a copy over there. So this paper, again, I think a lot of simulations, they design a lot of interesting things. And you can see that, like, say, because I know some of you, like the projects that you're doing are probably trying to reinvent the wheel in some way, that you're trying to say, okay, I have this problem in mind. I want to see, even without looking at like an academic, like existing paper, I might want to develop things by myself. So this, again, can be a good, like, I think, guide as what you can do. I mean, nothing is too fancy. It is nice paper, and then like a lot of technical parts there, but you can see how they develop it through step by step, right? Like they have this idea in mind, and then they talk about this example 1, example 3, I mean figure 1 and figure 3, and then things are not like more advanced, but they're still like, they were able to develop those simulation studies to say like, yeah, to support what they think. Okay, so those will be, if you want to try that, that will be definitely a good approach to your project as well. All right, okay, cool. So we're gonna end here with the discussion, and we have about 30 minutes left for today. So I was saying that if you have started using, doing the homework question, like the second question, I think that will be great, because if you have started, you will realize, so let me bring up something that I want to talk about related to that. So remember, in this particular MCMC diagnostic stuff that we have done, yeah, this part. So if you have started, so if you brought the textbook with you with the question, that would be great. So let me just restate it and then put it into the context of why I think this particular slide would be useful. Okay, so hopefully I have started. And you can, yeah, you can jump in to describe the problem if you want, for sure. So it's question 6.5, no, 6.2. It's mixture model, okay? So from the name, you realize that it's multiple components, right? But for 6.2, it's slightly simpler, because if you read it, you will notice that they only have 2 components over there. So in the example that I gave for the MCMC diagnostics, we have 3. Right, you have 3 different normals that you're drawing from, but then for the 6.2, it's only 2. Okay, so they're talking about the glucose data set, and it contains the plasma glucose concentration of 532 females from a study on diabetes. Okay. So I will jump into part B directly, just talk about how they came up with the mixture idea, and then try to make the link to what we have seen so far. So part B, consider the following mixture model for this data. For each study participant, there is an unobserved group membership variable xi, which is equal to 1 or 2, with probability p and 1 minus p. If x1 equals to 1, then the yi follows the first normal with mean theta 1, sigma, and variance sigma 1 squared. And if xi equals to 2, then the yi follows the second normal, which is theta 2, sigma 2 squared. Okay? And then they start putting on different priors for all of these parameters, and then ask you to derive the full conditional distributions for all of the i's from 1 to n, the p, which is the probability of whether you're going to go to the first component, and y minus p is going to the second component, of course. And then you have theta 1, theta 2, sigma 1 squared, sigma 2 squared. So all of those, especially the last four, about theta 1, theta 2, sigma 1 squared, sigma 2 squared, those are related to the normal model that we have done before. Okay, so if you have done part of the derivation yourself, you realize that it's not that different from what we have seen before. Okay, it is still under the normal gamma normal, the full the conjugate case that we have seen before. Okay. Anyway, so this is the context, and I brought up this page from previous lecture because this is how back then we're saying that you will be able to derive the full conditional for the indicator. Okay, so back then here the indicator is delta, and delta can be 1 or 2 or 3 because you have 3 different components. Let's see, 3 different components. And say in here, in order to come up with the full conditional, you're using Bayes theorem. Okay, on the top, it's like the data evaluated at that point times the prior. In the bottom is the sum of all of those. So this will be super relevant if you try to derive the full conditional xi in the new question over here, because xi is either 1 or 2. If xi is 1, meaning that this particular ith observation, we should put it into the first group, okay? And then if xi equals to 2, we should put it in the second group. Okay, so this is, I just want to point out that this particular slide, you will find it useful for getting the xi's, okay? All right, yeah, so I'm saying that like this is just a big picture, and then all of this will also be considered as the latent class modeling. So if you read the question, they're saying that you can like assume that each study participant has an unobserved group membership. Okay, so this unobserved membership, you can think of it as a latent variable that you don't observe, but it's underneath. You don't observe it, but you believe that it's there. So this latent class idea is saying that even though we don't know exactly like which, so first of all, they assume that below what we observe, there is a set of latent classes, okay? And each observation gonna be belonging to one of the latent classes. This is the general idea. So in the 6.2 question, it's gonna be, you have 2 different latent classes. Okay? You have 1 and 2, each of them is gonna be a normal, okay? And then you have this particular indicator, xi, to tell you which latent class it goes to. Okay, if xi equals to 1, it's going to go for the first one. If xi equals to 2, you're going to go to the second one. And then lastly, you need to have this probability, which is p in this case. Because you have 2 latent classes over here, you need a probability to assign for each of the observations.
I tried to start homework, but I couldn't really figure out problem 1. So I feel like I'm also.
Oh, 6.1?
Yeah.
Okay, yeah, okay, I will get, I will get to that. So let me just maybe spend just 2 more minutes about like the setup over here, and then I will walk around, because I was hoping that people have done some of this and then you can start doing the coding or like asking specific questions. But this is related to the latent class modeling that I talked about. So I just want you to spend just 2 more minutes on this. So, okay. Right, so here, so let me try to use the notation that they have. So they have xi goes to 1 or 2, okay? So if it goes to 1, it's gonna be in group 1. If it's equals to 2, it's gonna be in group 2, okay? So this is at the latent level. Yeah. And then once you know which group it's gonna go into, you see that the data gonna follow. So the data gonna be yi, right? Like that's the observation. That's what they use in the notation. So they say that if, so pretty much what this is saying that given the group assignment, say if it's 1, and then you're gonna know that it's gonna be a normal with means theta 1 and variance sigma 1 squared, okay? So what the model set up, and then if yi, if for some reason it get clustered into the second group, it's gonna be, yeah. So I'm trying to write out like the general likelihood for you. I wouldn't write it out in terms of like the probability, but this is the setup over here. So what else is missing here? We know that, so this is the, like, this is the likelihood. And you notice that we have this latent class assignment xi for each of the observation, right? So we know that each of the xi, I wrote it on the top already, but you can think of this as 1 with probability p, because that's what you're given, and 2 with probability 1 minus p, okay? Right, so this is a binary, okay? You can think of this as a Bernoulli. So this is what you know from the question. And yeah, so this is likelihood, this is latent, but once you introduce this, you should consider this as one extra parameter, right? And then in the end, you will have all of the priors. Okay? So they give you priors in here. They give you P is beta, which totally makes sense because it's a success probability. It makes sense to use the beta distribution to model it because beta distribution is between 0 and 1 and it's continuous. And what else? You have theta j is normal. So this is the prior for theta j. J is 1 or 2. So they put this, oops, they put the same mu 0 and tau 0 square. Okay. And then 1 over sigma j square, which is the variance. Oh, sorry, the inverse of the variance. They put a gamma. Right. And then they tell you what are the numbers for those, like values for all of this. So I was just trying to say that this is the setup. Oh, yeah. Mm-hmm. Yeah, so P is a probability, right? It's the whether, like P is the probability that like the observation xi gonna go to the first group, right? So this is in part, like this is in the model itself, right? And it is, so the setup over here is saying that instead of thinking of it as a fixed value, I want to also make inference about this because I don't know, like I don't believe it's gonna be a fixed probability. I know it's a probability, but I don't think it's a fixed number. So I'm gonna put I'm putting a prior on this, thinking that I will want to use the prior and the data to make inference about this particular probability telling me on average each observation, like with what probability should go into the first component. Yeah. So because that's what it is, right? I mean beta, so beta, you see that, so like FP will be proportional to P to the power of A minus 1, is that right? Yeah, and then 1 minus P raised to the power of B minus 1, right? Yeah, and then you factor everything. So what I was trying to say is, this is the beginning. Like you set it up in this way, and now you should try to write out the joint, right? The joint of all of the posterior. So we have done this before. This one is just, we had one more layer of this latent class, but you will need to put it into it as well, and then come up with the full condition of it. So together with like 6.2 and 6.1, I will go to 6.1 in a minute, but all of this exercise in terms of like deriving the full conditional, the first approach, I mean, the right approach, I think the first step is to write the likelihood like this, to put out the prior like this, and put everything together. That's like what we did before for the conjugate case. But now, because we're doing Gibbs sampling, we're trying to come up with full conditional. So in the past, we're trying to come up, say, if you're doing like theta given sigma, et cetera, but now, say, for the full conditional, let me use a different color. So once you move to the full conditional, what you have, I need to get, say, xi, given everything else, to follow something I need to come up with, okay? And then what else? P, given everything else, should follow something. Theta j, given everything else, we know it should follow a normal, right? Because the prior is a normal. Once you do it, you realize it's a normal. And then what is it? Sigma j squared, given everything, should be inverse gamma, because we're like writing in terms of sigma squared. But if you write 1 over sigma squared, it's going to be a gamma that we have done before. Okay, right. So the xi over here is going to be something very similar to what we have seen. It's going to be using the Bayes theorem. On the top of evaluating, say, okay, I have to bring it back later. I don't want to erase everything. So keep in mind, this is going to be what we have seen in the 3 mixture normal case that we have seen, like that particular slide that I was trying to show you. Okay, so this I think will be the newest material to all of this. And P, once you derive it, I think it's a beta. Yeah. But you need to collect all of the terms. So again, all of this is very involved. You need to write out the full, like the joint altogether. And then for each of the full conditional, collect any terms related to the stuff that you're working on. And then that will be the answer. So you should be able to recognize all of them one by one. Yeah. Mm-hmm. Okay, good point. So this one, I mean, because this one is really kind of like a lot of material. So if you don't mind, I can show you how you can set up 6.1. Okay, yeah. So I can show you like really quickly here how you can set up 6.1. All right, so I'm going to clear this and let me demo a little bit with 6.1 because it's slightly shorter. Okay. So it's talking about Poisson population comparisons. They are having 2 different groups and they parameterize with theta b. Okay, so over here. Theta b is theta times gamma, okay? All right, and in this parameterization, gamma represents the relative rate of theta b over theta a, and the is gamma theta b theta, and then okay, so these are the prior. So, I mean, we don't have to worry about A. Let's maybe just jump into full conditional. So you see that part B asks you full conditional for theta given YA, YB, and gamma. And part C is asking you to get gamma given YA, YB, and theta, right? So this is all full conditional because now it's the parameter that you're working on given everything else, okay? So how can we set this up? Oh, don't forget, the likelihood is Poisson. Okay, that's what the question tells you. Okay, so in order to set it up, we know that we should first of all come up with the, say like the joint, right? So the joint gonna be, part of it gonna be from the likelihood. So what's the likelihood? For group A, you are having all of them following a Poisson distribution with parameter theta, right? That's what the question tells you. So notation, let me see. Okay, so let me use YA1 until YA, did they tell you how many are there? Give me a second. Anybody did this so you know the count? Can you say that again? Sorry. So theta, let's see. Oh, it's gonna, okay, sorry. It's gonna be directly from the data. I guess I don't remember. So let me use N1 to represent how many observations in the first data, like in the first group. So what you know is this gonna be Poisson of theta, right? And all of the YB. So here I'm gonna use N2 to represent the number of observations in group B. It's gonna be Poisson. You know that's gonna be theta times gamma. Okay, so the likelihood YA1 to YAN1 will be, because they're IID, it's gonna be product I from 1, in this case A1, right? And then the Poisson density. Anybody remembers? I just don't remember those Poisson density. Anyone? Okay, I got it. Sorry about it. Let me just go. Okay, so this one will be e to the power of theta, and then theta raised to the power of YAI, I guess, divided by YAI factorial. That's just the density from Poisson, okay? And I'm producting all of them over here, right? Okay, and then the joint of B1 until Bn2 will be I from 1 and 2. So here is e to the power of theta lambda, because, sorry, not lambda, gamma. Gamma over here, right? And then over here is theta gamma raised to the power of YBI divided by YBI factorial. Okay? Yeah, did I make a mistake somewhere? Yeah, good point. Yeah, I just realized I didn't write everything clearly. So here, yeah, the good way to write it, like the correct, more formal way, is this going to be, because this is the likelihood. It should be given theta, yeah, just given theta, I think, over here, right? And then down here, it should be given theta and gamma, right? Yeah, because this is like the Poisson, the rate of it is theta times gamma. So you're conditioning on both parameters. Oh, it's the same. It's the same. Yeah, but I will prefer, I mean, personally, I think I would like to write all of the parameters separately, because in the end, you will try to derive the full conditional for them separately, right? Okay, so this is the data, like the likelihood. And the prior you're gonna have, so the joint prior is gonna be about theta and gamma, right? Oh, not gamma, lambda, gamma over here. Yeah. So what do you have? You have the marginal of theta and marginal of gamma, right? And I think they're independent. So pretty much you just have this times this. Each of this is a gamma. So you're just going to use the gamma density, which again, I need to look for it. Gamma, okay. Yeah, so I would just write a proportion over here because some of them are constants. So for theta, because it's gamma, A theta and B theta, so it's gonna be e to the power, let's see, e to the power of, anybody remembers? I think the note, yeah, because the text, this book is using a different implementation. Give me a second, sorry about this. I want you to keep consistent using what we have done. Oh yeah, that would be great, thank you. Okay, so because it's a gamma, okay, so it's proportional, so it's theta, so it's gonna be, yeah, let me write it step by step. Yeah, so it's, because it's about theta, and the first parameter is A theta minus 1, okay? and in E, negative B theta times theta, okay? And then you do that the same for gamma. So it's gonna be gamma raised to the power of A gamma minus 1, and then E to the negative B gamma times gamma, okay? So those will be all of the terms. I think the likelihood is here, the prior is here. You're gonna, just like what we did with the conjugate case, you put everything together and then try to find the terms related to, in this case, you only need to find two. One is theta, the other one is gamma. It's the same, right, yeah. So yeah, you multiply this together. Say, I mean, just maybe really quick, just to demonstrate, say how to get theta, the full conditional, you just gonna find whether relevant, 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 right? Yeah, so just put all of this together. And don't forget the product, okay? Because things are product, like, yeah. So I'm just writing in the short form that I'm writing the product and each of them is like each density, but you should write it as a joint, okay? Yeah, and then the same goes for the gamma, right? So what's relevant? This is relevant, this is relevant, this is relevant, and this is relevant, right? So keep in mind, this is different from the conjugate case that we're trying to do before. Like, remember with the normal case, if you have used it before, we were saying that, like, don't keep it there, right? Because we're still getting the joint. The product should be the joint, or like the joint should be the product of those two. But here we're doing full conditional, so you can reuse terms. So that's what I'm saying, like those terms, like this one and this one, you use it twice, but that's fine because you are doing full conditional. Full conditional says that it's given everything else, okay? So don't get yourself confused. And I think, to be honest, I think once, yeah, like now, since we're doing Gibbs sampling, we're just doing full conditionals, everything is easier because you don't even need to worry about like those extra terms that you bring into, or any terms that you have used, do you have to delete it from the next step, okay? So yeah, so pretty much all of this, yeah, so I think the full conditional, once you have done it, it's gonna be two gammas, not surprisingly, right? So you start with the prior, theta and gamma, both of them are gammas, gamma distributions. Once you derive the terms, like collect the terms and then try to derive it, it's gonna be two separate gammas again. But of course, in it, like the term, like the parameters are different. It's gonna be associated with the data, associated with like the prior, et cetera, et cetera. So once you do it, yeah, it's gonna be two different gammas. If you want, you can like email me to check if you get the right answer. But I think as long as you follow all of the steps, like nothing will be too surprising. Yeah, it should be two separate gammas based on the derivation. Okay. All right, cool. Anything else? I mean, I also would like to talk to each of you like quickly about the projects. But if you like, I mean, you can break into groups if you want to talk about all of this, or maybe try one of those, or if you have started doing of either question, if you run into any of the problems to answer as well. But in the meantime, yeah, we'll have 5 minutes left, so I just really want to. But you can talk to each other. Right,